that video would just be that one problem. All right. What do you guys want to look at? Was that it? I mean, does that help?
I think I understand the circuits from this last week. Can you? I was so confused by simplifying circuits.
Uh-huh.
Equivalently.
Oh yeah, we could do that.
I was wondering if you could do something small.
Yes, I can do some of those. Let me try to find one that's in the list of the recommended. So we're talking about chapter 26 maybe like numbers 11, 23 maybe. No, that's still complicated. Let's do 16. I don't know if I assigned that one or not, but I think it's what you're looking for. So this is number 26.16, which is on page 899. So you got a 6 ohm, and down here you've got an 8 ohm, and those are in parallel and they're in series together with this 25 ohm, and all of that is in parallel with a 20 ohm, and then all of that is put across a voltage source, which they call E. And what information are we given? Well, we're told that there's 4 amps flowing through the 6 ohm resistor, and then ask the question, what are the currents in the 25 ohm and the 20 ohm resistors then? This is a nice question. This is a good way for me to test almost the same physics as the last problem that took us an hour. You know, I can almost test the same physics with this one without burdening myself with trying to sort through how you guys messed up 3 equations, 3 unknowns somewhere. So anyway, significant partial credit is given for that past problem if you set the equations right upright, you know. So, but I do make a significant part of the credit finishing the problem correctly too. So it's not like you can just kind of well, I'm not going to learn that. You do need to learn it.
The 4A is the current going through the 6 ohm.
Just the 6 ohm. So the equivalent resistance idea, right? Let's do that. So basically, we can look at this as I'm gonna kind of draw it symbolically. We've got the 6 ohm paralleled with the 8 ohm, right? And that is in series with this 25 ohm, right? And then that is in parallel with this 20 ohm down here, right? So that's the first thing. And then so what that really is the same as if they're in series, we just add the resistances, right? So we have our 6 ohm paralleled with 8 ohm plus 25 ohm. And that is in parallel with this 20 ohm. Now let me go ahead and figure out the value of that top one before I go any further. How do we find what's the formula for this? We do 6 times 8 over 6 plus 8, which is 14 ohms plus 25. What's that? Nothing too pretty, is it?
Is that the same thing as doing the 1 over 6 plus 1 over 8 reciprocated plus 25?
Yep. 28.43, I'll take 2 digits here, ohms approximately. So yeah, that is 6 times 8 over 14 is the same as 1/6 plus 1/8 reciprocated. And that is, let me just double check on it. Three point 3.429, or if you, no, let's say 3.43 ohms is what that is. About 3.43 ohms.
Yeah.
All right. So then my equivalent resistance, not that this problem actually asked about it, but let's figure it out anyway just for kicks. The equivalent resistance, and I don't think you actually need to figure out the equivalent resistance here to do anything. I'm just figuring it out because, you know, it's fun and you asked. So I would do, 20 ohms times my 28.43 divided by the sum of those two, which would be 48.43 ohms, I get 11.74. 4 ohms is like the equivalent resistance of, if you put all of this together. Does that make sense?
Or if say this was capacitors instead, it would be the opposite.
Yeah, capacitors would be the exact, it's all, yeah, the other way. Let's see if we can solve the problem though, because this doesn't really help us solve the problem, does it? So to solve the problem, we just need to use some basic circuit analysis ideas. So like, for example, what's the voltage here, plus to minus? It's I times R, right? Which in this case is 24 volts. Why? Because I've got 4 amps, I got 6 ohms, IR, 24 volts. And if that's 24 volts, that means that I can then figure out, because those are in parallel, the same voltage must be applied across the resistor right below it, right? So, like, sorry, I'm trying to find a particular color. Where'd it gone to? So, right here, we must have I through the 8 is going to be what? It's going to be, 24 volts divided by my 8 ohms, right? Which is 3 amps. So I have 3 amps going through the 8 ohm. But then what happens? If I've got 3 amps going through the 8 ohm and I've got 4 amps going through the 6 ohm,
There's 7 amps going through the...
right. 7 amps going there. And then what else can we answer? Oh, if that's the case, then how much voltage is there here? So you've got 24 volts, right? Plus what? This voltage here, which is 25 ohms times 7 amps, right? So that's 175 plus this. Yeah, 199 volts. The circuit's kind of dangerous.
That's for everything.
Yeah, from here to here.
Total volts going from everything.
So basically this is a 199 volt power supply is what it boils down to. And once you know that, then we can figure out what's the current through the 20. Right? What's the current through the 20? Well, the current through the 20 must be equal to 199 volts divided by my 20 ohms. Whatever that is. 9.95 amps. You guys want to do some more equivalent stuff?
No, that makes sense now. I just needed one example.
But you want to see a capacitor one?
Oh, actually, I do want to do that.
Yeah, let's do one. See if I can find one of the recommended homeworks to do. Oh man. Oh, that's right, it's earlier. I keep thinking the capacitors are later, but they're earlier. Let's see here, 2421. Perfect. This is what we want. Ooh, double dots, double blue dots. This could be too hard for me right now. I don't know. You know? Double blue dots. Very troublesome. 2421. All right, so for the system of capacitors shown in this figure, which I will draw out here. So you got node A, and then we've got up here a 7.5 nanofarad capacitor. And then in the middle branch, you've got yourself a 18 nanofarads, 30 nanofarads, 10 nanofarads, all in series. And that is in parallel with another 6.5 nanofarad capacitor down here. And all of those come over here to node B. So you got node A, node B, and we're told that VAB is 25 volts.
What is a capacitor? Like, what does it do?
What does a capacitor do? It stores charge on two plates by, it's got two pieces of metal that are separated by some insulator, so that if you put a positive charge on one plate and a negative charge on the other, you can store energy in an electric field between them. So it's a way of storing charge, basically. That's the short answer. But more generally, capacitance is a property that any two conductors have relative to each other. The question then is, what's the equivalent capacitance of the system between A and B, which was like your question, guys, right? And then the question is, how much charge is stored by the system? And then the question is, how much charge does the 6.5 nano capacitor store? And then the question is, what's the potential difference across the 7.5 nanofarad? What's the potential difference across the 7.5 nanofarad capacitor? Well, duh, George. Like, come on, it's 25 volts, duh. This book sometimes asks dumb questions. So, anyway, right? I mean, like, look, what's the voltage from here to here?
Yeah.
It's given to be 25, so yeah.
So there's 25 volts going through each one of those three.
Voltage doesn't go through things. Voltage is relative to 2 points.
Okay.
So,
Okay.
yeah.
So
But, yeah. Equivalent capacitance then, right? So we'll start out with, let's just figure out the middle branch. That's the easiest, that's the kind of the big one here. So we do 1 over 18 plus 1 over 30 plus 1 over 10, inverse of all of that, nanofarads. That's the, this is the equivalent capacitance of the middle branch, right? So whatever that works out to, let's work it out. All right. We get 5.3-ish, so 5.2 0.294 nanofarads. All right, so essentially, this is the same as if you've got 3, right? You've got 7.5 nanofarads in parallel with your 5.294 nanofarad equivalent capacitor to the middle branch. It's cool that the equivalent capacitor notion, like you can keep applying it in stages, you know? It's a very forgiving concept in that sense. It's cool. And then now they're all in parallel. We like this. So in total, the equivalent capacitance is 7.5 plus 5.294 plus 6.5 nanofarads. So C equivalent is I get 19.29 nanofarads, something like that. Now this is an odd problem in the book, which means that I can check it, and I will foolishly now check it. 24, 21, 19.3 nanofarads. Hooray. Oh, by the way, the answer to part D is 25 volts. Did we do this one already? I feel like we did this one already. Dang it. All right, well, I'm going to stop doing this one. Should we do a different one? Oh, man. Son of a gun. What about 28? Did I do 28? It's like this is starting to feel really familiar. These numbers felt familiar.
24?
I think I did I did 28 too. Yeah, we did 28 as well. Yeah, I think we did. Pretty sure.
Yeah, we did.
I bet we didn't do 53.
I think we actually did do 53.
Oh, man.
We did do 53.
Oh.
But that one, honestly,
Ah. So we did 53. What about 51 though? We didn't do 51.
no.
Yeah, all right. And 51 should address any confusions that came up in 53. We did find the answers in 53 though. We checked at the back of the book, right?
Yes.
So. Maybe 51 will help. Let's see here. All right, so 51's another equivalent capacitance problem, but it's also got energy involved. So,
I have a question.
Go for it.
So, if there's a capacitor on one branch, does there have to be a capacitor on all the other branches?
No.
But if there was a capacitor on the other branches, would that capacitance be zero then?
What do you mean? If there was a capacitor?
Like, on like the example you did just before this, like the 24.21.
Uh-huh.
What would the answer, how would it change the C equivalent? How would that change if, for the second part, how would that change if you just didn't have anything on the top branch? If the 7.5 wasn't there?
You mean if it was just a wire?
Yeah.
Well, that is a fire. Like that's a bad problem. See, because at this point, according to the rules of our circuitry, this has zero resistance. But then we've got VAB is 25 volts. So you got, what's the current going through this branch here? Well, the current would be VAB divided by 0, which is infinity, and infinity makes a fire.
So there has to be something.
Yeah, there has to be something there. Yeah. 8.6 microfarads, 4.8 microfarads, 3.5 microfarads, 6.2 microfarads, and 11.8, you guessed it, microfarads. And we're told that the voltage from A to B in this character here is 12 volts. And we're supposed to A, find the total energy stored in the network. Total energy stored. And then B, energy stored in the 4.8 microfarad capacitor. And this again was problem number 2451. 2451. All right. So just to tell you the solution method, what we do is we simply find the equivalent capacitance and then use one of the energy formulas for that. And I think we're going to use the 1/2 CV squared because that's the natural choice, right? Like, because we'll know the capacitance, we'll know. So all right, let's get to it. So what's 6.2 microfarad in series with 11.8 microfarad? It gives me what? 6.2 times 11.8 divided by, add those two together. 18 is what? Denominator. I'm going to call this C top. The top. What you got? What you got for me? 6.064? Oh, 4.064? All right. We got agreement? And then, so you've got this C top paralleled with 3.5 microfarads, and we'll call that C right. CR. I'll just call it CR. And that is, 4.064 plus 3.5 microfarads. So that's the right resistance, let's say. 4.064 plus 3.5, we get ourselves a 7.564 microfarads. Let me illustrate pictorially what's going on here. That is all of this. I'm calling CR. And then we have C equivalent is equal to what? It's equal to 1 over 8.6 plus 1 over 4.8 plus 1 over CR, which is 7.564. Invert all that stuff, and slap a microfarads on it, because that's what's going to happen. Now, gotta be careful. If some evil professor throws some nanos and some micros together, you gotta keep track of that, right? What's that?
I was saying you just had to convert them.
Yeah, you have to convert. I mean, pick your poison.
I got 2.19.
2.19 microfarads. Excellent. Now, that seems reasonable. Let me explain why. Remember, when we put the capacitors in series, the value of the equivalent should be smaller than the smallest one. All right. It's just like resistors in parallel. It is kind of neat how these problems are dual. Like, it's the same math, but like the rules are reversed, right? It's kind of neat. So to do part A, the energy is 1/2 CV squared, which is 1/2 times 2.19 microfarads times our 12 volts. Square that thing. What we got? Ah. That is what I got as well, 157.68. And the units here are microjoules. All right. Let's check. 158 microjoules, yay! Now part B. How do we figure out the energy stored in the 4.8 microfarad capacitor?
Is it not just the same thing, but C is 4.8 instead?
But what's the voltage there? It's not, no. It's not 12 volts, no. So we can't do that. But remember what we talked about is that the capacitors that are in series share the same charge, right? So I could think of it this way. This has got a Q minus Q, Q minus Q. You know, all of this together is Q. All of this together is minus Q. I don't, you know, that it gets parsed up in there. Who cares? But the point is, you can figure out the Q. Remember C, how do we get Q from, I always have to go back to this. C is equal to Q over V, right? So Q is equal to CV. So C equivalent times the 12 volts, that gives me the charge. That's on this one, on that one, and then it's parsed between these.
Yeah.
But hey, it asked us not for any, just which one it asked. It asked us for the 4.8. So yay, we don't have to worry about the parsing of the charge over here. We can figure it out directly from this. So this is what? C equivalent times 12 volts, which is 2.19. So you got whatever that is, 2.9. 2.19 times my 12. I get 26.28 microcoulombs. Now that doesn't tell me the energy, but how do I figure out the energy then? Remember, there are 3 formulas. Each have their place. So we don't want to use 1/2 CV squared because we don't know the voltage on the 4.8. We don't want to use the 1/2 QV because, again, we don't know the voltage on the 4.8. But the Q squared over 2C, that's the one. So Q squared.
Can you say that in 3 equations, please?
Yeah, I'll write them up here. So the potential energy on a capacitor, we have 1/2 QV is Q squared over 2C is 1/2 CV squared. These are the, potential energy in capacitor. It's the energy stored in the electric field, as we were talking about last class. So we just Q squared divided by 2C. Now the C is the 4.8. So, we get 26.28, square that thing, and divide by 2 times 4.8, which I think is 9.6. And I get 70.47. 70.47 microjoules. So this is 4.8 micro. Which, thankfully, is 72.1 is the answer they give, but there's significant figure quibbling. That's what that is.
So you said the charge
Mm-hmm.
for each system would equal what was it, 2.19?
So when capacitors are in series, they share the same charge. So effectively, the equivalent capacitance also has that same charge. There is 26.28 0.28 microcoulombs on this capacitor, on that capacitor, and it's shared over here. I'm not sure how much on each one of these, but the sum of the charge on this and that is 26.28 microcoulombs. And whatever the charge is on this one, it's the same as the charge on that one because they're in series, whatever that is. To figure out what that is, what I would do is I would figure out the voltage on this one, I'd figure out the voltage on that one, and then I could figure out how much voltage is actually over here. Then that would tell me what the voltage is on this. I could figure out the charge which was on that, and then I'd take that and subtract from 26.28, which would then tell me the charge on this and that. Once I know the charge on all the capacitors, I can figure out the voltage on all the capacitors as well, or vice versa. If you know the voltage, you know the charge. If you know the charge, you know the voltage. That's the part and parcel of this relation. The capacitance is the ratio of the charge to the voltage for the capacitor. So if you know the charge, you know the voltage. If you know the voltage, you know the charge. If you know the capacitance, they're connected by that formula.
So if we need to find the energy on the 8.6, it would just do the same charge divided by 3 times that, right?
Right, yeah. So the energy on this one, you could just do 1/2 times 26 point, whatever that was, 28 microcoulombs, square that thing, and divide by your 8.6 microfarads, and whatever that would be, yeah. That is true. Do you guys have other questions?
I'm also probably gonna leave
That's cool.
soon.
That's fine. I think that's probably a decent place for us to stop today anyway, so we'll call it quits here. I try to do more examples, generally speaking, but I'm just kind of low energy at the moment, so it's probably